The goal for 3.1 is to solve basic one-step equations. Most of it you'll probably have seen before, like addition and subtraction equations and multiplication and division equations. We'll probably spend a little more time on fractions and reciprocals, and then as always we're going to check our answers. Inverse operations are operations that undo each other. Pause the video and list what you think the inverse operations are. So addition and subtraction, multiplication and division. And then the other one that it's still inverse, but we don't see it too often in this section, is if something's being squared and square rooting. Those are inverse operations. Properties of equality, I think of like a seesaw. So if you can imagine that a seesaw is balanced, basically what the properties of equality say is that if you add something to one side, as long as you add the exact same thing to the other, it's going to stay balanced. Or if you subtract something from one side, if you subtract the exact same thing from the other, it will stay balanced. Same thing with multiplication and division, which is why the golden rule of equation solving is that whatever you do to one side, you do to the other. The big thing with equation solving that we're going to hear about all year long is that anytime you're solving an equation, your goal is to always isolate the variable. Get the variable by itself. That's when you're done. So together we're going to solve a few of these basic equations together, and then I'm going to have you pause the video and do the rest on your own. So if you look at just the first one, we know our goal is to isolate x. So the thing that I ask myself is, what's bothering x that I need to get rid of? And in this case, it's 7. What's 7 doing to x? It's adding, so to undo addition, I would subtract. So I minus 7 from both sides. The reason I do that, 7 minus 7 is 0, and then x plus 0 would just be x. So now x is isolated. I always bring my equal sign straight down. You can draw the line if you want, but you don't have to. But again, the equal sign always has to come straight down. And then x would equal negative 3. So that's my answer. I know I'm done because x has been isolated. So if I move on to this one, same approach. I need to get the x by itself. It's being bothered by a minus 12. So to undo that, I would add 12 to both sides. The reason that gets rid of the 12 is because this one right here is really like a negative 12, and then a negative 12 plus 12 would be 0. And then again, x plus 0 is just x. So x is by itself, and then in this case, x would be 15. This one's a little bit different over here, the 19 minus x, because the operation is subtraction, so a lot of people think that to undo it you would add, but if you added 19 right below that, you would get 38. You wouldn't get 0. So to get rid of the 19, what we actually have to do is minus the 19. So now 19 minus 19 is 0. So if you think of it like this, it's really like a 0 minus x, and then 5 minus 19 is negative 14. But then 0 minus x would just be negative x. I still haven't isolated my variable because I have that negative sign in front. So what I want to do is figure out, I don't want to know what negative x is, I want to know what positive x is. It's pretty easy. If negative x is negative 14, then positive x would be positive 14. So what you're going to do, you're going to pause the video, and you're actually going to give these problems down here a try. So the negative x plus 4, then negative 6x equals 48, and the x divided by negative 4 equals negative 7. Always start by asking yourself, what's bothering x and how? So how can I get rid of it? Like up here it was plus 7, so I minused because that made it 0. So that's always your goal. Pause the video, give those a try. So if you look at these examples, hopefully you got the answer that x equals negative 11, x equals negative 8, and x equals 28. On this one, just to talk about why, so negative 6 is multiplying x. To undo it, we divide. The reason that works is because a negative 6 divided by the negative 6 over here would be a positive 1, and then 1 times x is just x, so that actually isolated x. Over here, we multiplied both sides by negative 4. I just did it off to the side, and the reason for that is if you actually put the negative 4 over 1, don't forget that when you multiply fractions, you're allowed to cancel diagonally. So your negative 4 and your negative 4 would actually cancel out, and you're left with x all by itself. Go on to the next slide. So these examples are a little bit different. So here you have negative 2/7 that's bothering x, and the operation between them is multiplication. So normally you would divide by negative 2/7 because that's the inverse operation of multiplication. But on this side, if I was going to do 4 divided by 2/7, how do you divide fractions? You multiply by the reciprocal anyway. So rather than actually divide it all I'm going to do on both sides is I'm going to multiply by the reciprocal, which is negative 7 over 2. And then whatever I do to one side, I have to do to the other. So I'm going to put negative 7 over 2. And if you cross cancel, your negative 7s would cancel and your 2s would cancel. So you're actually left with x all by itself. Then I could put 4 over 1, cancel my 2 with my 4, that would become a 2. X equals negative 14. You would get the same thing if you had divided by negative 2/7, but it's just kind of a shortcut. Try the shortcut with the next 3 examples right over here. Pause the video to do that, and then check back in to see if you're correct. So if you take a look at this example, I multiplied both sides by 6 over 5. Don't forget that the 5 and the 10 can cancel before you multiply across. On this example down here, the reciprocal would be negative 4/3. So that's what I multiplied by. I just put it over here because it was honestly easier to write it, but the 4's would still cancel and the 3's would still cancel. And then over here, don't forget your 3 and your 9 can cancel, and a negative times a positive is a negative. Don't forget that. And then over here, the reciprocal of negative 4/5 would be negative 5/4. Multiply both sides by negative 5/4, and you end up with a positive 10. This is probably one of my favorite examples right here, so give it a try, see what you get for an answer, pause the video, and then come back. So in this example, the number that we needed to get rid of that was bothering x was 9. It was multiplying, so to undo it, we divide, and 3 divided by 9 is 1/3. The best we can do is reduce that. If you got 3, think about it. If you put the 3 in for the x, 9 times 3 would be 27, not 3. Also, 9 can't fit into 3 times, so 3 over 9 would just reduce to 1/3. You don't want to use a decimal, because if you did and you actually plugged your decimal into check, no matter how many decimal places you used, it would never come out to exactly 3. It would be like 2.999999. So you always want to use fractions when possible. So in this example, we're going to highlight the important information. So in the 2004 Olympics, I don't care what year it was, Sean Crawford won the 200-meter dash, so that's important. And his winning time was 19.79 seconds. And it's asking us to find his average speed. So we have a distance, we have a time, and speed, which is synonym for speed, is rate. So as soon as I see those 3 variables, d, r, and t, the equation distance equals rate times time should pop into my head. And then I can plug in the things that I know. So the distance is 200 meters, the rate I don't know, and the time was 19.79 seconds. So you're going to solve this equation for r. So if you solve this equation by dividing both sides by 19.79, hopefully using a calculator, you get that the rate was 10.1 meters per second. So now it's saying, what if you ran the 100-meter dash at the same speed, which we just found up here? How long would it take him to run this time? So again, we're talking about a distance, a rate, and a time, but this time the unknown is the time. So I'm going to replace distance with 100, the rate or the speed with what I just got, and I'm going to solve this equation for t. Pause the video and go ahead and do that. So when you solve this one, you would divide both sides by 10.1, and you end up with 9.9 seconds, which makes sense if you check the reasonableness of your answer, because up here he did 200 meters in about 20 seconds, and now he's doing about half that in about half the time. Scroll down to this problem right here, set up and solve that one, pause the video, give it a try, and come back and check your answer. So on this example, if you replace the distance with 50, the time with 24.8, to solve for r, you divide both sides by 24.58, and you get the rate is 2.03 meters per second.